This is page 6 of the communication notes, and it's section 5, and we are going to talk about queuing theory. So we've created bounded buffers. That was really the whole point of the last 5 pages of the notes, and they're used to communicate data between tasks. And the question is, how big do these arrays of buffers be? So if the consumer can operate as fast as the producer and will never be slower, then you really just need 1 or 2 buffers. But oftentimes that's not the case. So the production rates might not be linear. They might have a bit of randomness to them, and so on. And so there was an engineer in Copenhagen, Denmark, who was working on telephone systems, and he wanted to know for switchboards. So you used to have these patch cables that you'd use to connect calls, and the question was how many operators did they need, or how many circuits did they need to be able to handle the amount of calls that they would get without people having to wait too long. And so he developed some theory around that. The textbook has a section on this. It's 15.2. And with queuing theory, it models the world as a client-server system. So it models the world as client-server systems. And so examples of this could be clients lining up at an ATM, automated teller machine. The old example used to be, clients forming a queue and lining up in the bank to be served by a teller. Nowadays it's more likely to be an ATM. But anyway, so you can monitor the ATM, and you'll know on average how many people are coming over a period of time, but they won't arrive at regular intervals. So it's a random process. Another example would be requests arriving at a web server. Here is the picture. So clients arrive. Well, here's the words for the picture that's about to come. Clients arrive and wait in the queue to be served. Also, the service times may vary too, right, depending on the request. So one person at an ATM might take longer than another person. So the queue is usually drawn like this. Well, that's supposed to be a straight line. Other than that, that's how it's normally drawn. And so these are spots in the queue, and jobs or requests in the queue are processed by a server. And clients arrive, and clients can be jobs that need to be done at this end of the queue. So the client average arrival rate is called lambda, or is represented by lambda. So this is the average arrival rate, and the average service rate is mu. Now, we've been talking in terms of producer-consumer problems. So the question is the producer the server, or is it the clients? Does it represent the clients? So if you think about it, a producer is producing units of data that need to be consumed by the consumer. So it's producing things or jobs. So the The producer is actually modeled as a client in queuing theory, and the server is the consumer that's taking the data as it comes in and processes it. So the producer puts stuff into the queue, packets of data, and the consumer or the server takes them out and works on them. And we've got one more Greek letter here. Let me try that again. Okay, we've got one more Greek letter here, rho, and that is equal to the average arrival rate over the average service rate. And this is called the load factor. And this needs to be a number less than 1. If on average your clients are arriving faster than they're being served, then you're going to overrun your queue eventually. And we're going to assume a queue of infinite size for now. Makes things easier, and then we'll get to a limited size queue or a bounded buffer. So assume a queue of infinite size for now. Alright, so the arrival and the service rates can have a couple different types. So arrival and service rates can be one of a couple of things. So the first one is deterministic or predictable, and that's characterized with capital D. So clients arrive with regular interval t equals 1 over lambda. So they're nice and predictable, and that's going to be easier to model. And if it's a server we're talking about, the service time is going to be 1 over mu. Okay, next page.